Hello, so my name is Mohammed Saad and today I'm going to present the predictive modeling of concrete strength using advanced machine learning. So let's start it. So the project overview. The objective of this project, the main goal behind the project is to predict the comprehensive strength using material compositions, categorize strength into actionable classes low, medium, and high. Each explore clustering and ensure model reliability. The significance of this project is it will save time and the cost in construction. It will reduce the reliance on destructive testing. So this is how our model is going to work. We are going to take the data, then we are going to do the pre-processing, then we are going to do the modeling, and then it's going to be the evaluation. So first of all, we are going to have the description of this data set. So the data set consists of total 1030 samples. The features which we have in our data was cement, slag, ash, water, super plasticizer, coarse aggregate, fine aggregate, and the age. These are the things, the features which we use in our model. Like you can see here on the graphs, these are the histograms of the data which we have, and the target which we have was the compressive strength. That one is in the megapascal. So first we did the data pre-processing. In data pre-processing, we have handled the first step was to see if we have any missing values or not, but there was no missing values in our data. It was very much cleaner. So then we standardized the features using standard scaler. Then we detected the outliers visually but retained them from modeling. Then we split the data into training, validation, and the testing, and created then we created polynomial features for nonlinear interactions. Then we went on to the exploratory data analysis. So the key insights of this analysis was the cement and age are strongly correlated with the strength. Its aggregates are negatively correlated. A non-linear relationship exists between water and the strength. There was a non-linear relationship between them. Then the cement and age are priority features. Relationship requires nonlinear modeling. You can see it in the heat map that how all of the features are correlated. Then the next step was the models. I have selected the four regression models: the linear regression, the decision tree, the random forest, and the gradient boost check. The result was that in random forest, we achieved the best performance with the mean square error 27.84. And the insights from this analysis was random forest captures nonlinear interactions effectively. Gradient boosting showed competitive performance. As we can see it in the histograms, the residual on validation data, the residuals on training data, and this is how the data was split. Then I have uh, there are four classification models which I have incorporated in my project: the logistic regression, the k nearest neighbors, the random forest, and the decision trees. So the best result we achieved in was from random forest, and the F1 score for random forest was 99.9%. So then we evaluate the precision, recall, and F1 scores across all the classes. This is the confusion matrix of the analysis which we have done for the classification model. Then we have the clustering analysis. In clustering, the techniques I have used was k-means and hierarchical clustering. K-means identify three distant clusters based on material composition. The PCA reduced dimensions for visualization. Then I did some reliability testing. I did the cross validation, the five-fold ones, in which we divided our data into five folds, and then we checked the data one by one. The F1 score for the cross validation was 99.9%. So this is the histogram, the bar chart of the bootstrapped F1 scores, and this is the cross validation box plot. So then for bootstrapping, the mean F1 score was 99.8%, and the standard deviation was only 0.01%. That is very less. The noise injection performance dropped by 1.2%, and the feature ablation removing cement significantly reduced the accuracy. So then we are going to jump on to the importance of the features. So cement and age are the most critical features for predicting the strength, because the strength depends on the cement, like which cement are you using, also as well as the age of the cement. The polynomial features enhance nonlinear modeling capabilities. As you can see in the this bar chart, that it shows that the features important for from the random forest, the most important feature was the age and then the cement, then rest are like we can incorporate them. So then we jump to the results and comparison. So regression results was random forest was the best, the mean square error was 27.84. Then the classification results, random forest achieved 50, the F1 score of 99.9%. Then in clustering, we are going to identify meaningful groupings that align with material properties. So in as you can see in this the table which is given here, like we are going to compare all of the models: the linear regression, the decision tree regressor, the random forest regressor, the gradient boosting regressor, the logistic regression, the k nearest neighbors, random forest classifier, and the decision tree classifier. So out of all of the models, the best performing model was random forest classifier with the F1 score of 0.999%. So it's round about equal to 100%. So that was the best result which I have got. So we are going to jump to the conclusion. So the achievements of this project includes the accurate predictions and robust classifications. My project identified critical features like cement and age. Practical implications includes the enables cost effective real time strength predictions. It reduces risk in construction by optimizing mixed designs. The limitations which this project includes is the dataset lacks environmental factors like kerning conditions. So then we are going to jump to the future directions, like the future scope of the project. We can explore neural networks for enhanced accuracy. We can include environmental and geographical data. We can optimize for sustainability by adding CO2 emission as a metric. Then we can implement real-time IoT based monitoring for on-site predictions. So that was all from my side. Thank you so much.